Hey, welcome to the Art of Code. My name is Martijn, and I haven't made a shader tutorial in a while, and what you see behind me here is an effect that I did a while ago, and a couple days ago I decided why not just polish it up nicely and make a tutorial out of it. So in the next few videos we're going to make this thing from scratch, so if you are interested in that, then definitely stick around. Alright, actually I just realized that I lied. I'm not going to do it exactly from scratch. I'm going to start with a ray marcher, which is the basic 3D engine that we are going to make the entire effect in. I made a video specifically about how to make that actually from scratch. The link is in the description below. Yeah, so go check that out and then come back and you can follow along with this. So this is just a template. The link for the template is in the description. And this shows a simple ray marcher with a cube here that you can move with the mouse. Okay, so that's where we're going to start. Now let me just collapse a few things, a few functions that we're not going to look at right now. The ray march function as well. So this is the distance function. This is what kind of describes the scene, and right now it only has a box in it over here, and I'm going to get rid of that because I'm going to make a sphere. So the distance to a sphere is just the length of the the distance to a sphere that's at the origin is just this, the length of p minus the radius of the sphere. So if I do that, then I get a sphere, which is cool. And actually, let me just call this ball over here, and then because I'm also going to make a ground, and the ground is the distance to the ground is just the height of our current position minus the height of the ground, and because the ground is going to be let me see here, the ground is going to be below 0. I'm going to add 1 to this. Let me see if that works. So now I have the ball on the ground. I have to put them together. So I do that like that. Just take the minimum between the ball and the ground. And again, if you don't understand here what I'm doing, then definitely check out my other video on the building a ray marcher from scratch, because everything is explained there. So now I have a ball with a ground plane that is stuck at the bottom of the ball. You can't really see it at this point, but you're gonna trust me, because the entire coordinate system is relative to the ball. So the origin is right in the middle of the ball, which comes in handy for many things, as we will see later on. So now we have the ball and the ground plane. Now I'm going to add a gyroid to this. So gyroid is a minimal surface, a very contorted surface that is very easy to make, and you can use for many different things. I made a video specifically about gyroids as well. Also, link is in the description. But for now, I'm just going to make that more quickly. Actually, I'm going to put it over here. Call it float g, and then the gyroid is the dot product of the sine of some value p, or some 3D location p, and the cosine of that, but then swizzled so that the x, y, and z are turned around. And let me see here, z, y, x, I think, but we'll see if that comes out good. So let's see here. So let me cut that into the ball. So I'm going to go ball equals max ball and g. This is a Boolean intersection I'm doing here between the ball and the gyroid. And if I compile that, you can see that I have the ball is half cut right now. And what I have to do now is, because this gyroid is just too large, like the pattern, we need to compress the pattern. And for that, I am going to Actually, let me just put this into its own function. So I'm just going to take this out here, cut, and I'm going to call this ball gyroid, and I'm going to throw my position into it, and it's going to give me the distance back. So I'm going to go over here, float, ball gyroid, with a vec3p position, a 3D position, and then I can be inside of here, and I can just return that. And the reason why I did it like this is because now I can go over here and I can compress this. So I can just, if I multiply this by 10, and then my entire gyroid is 10 times as small. And when I do that, I get this, and it has a lot of errors. And the reason why is because if I compress something, then that means that the distance that comes out of it also needs to be adjusted so that it fits the same compression as over here. So that should be better. And this tells me I got the swizzle wrong. So let me see here. Y, ZX. Yeah, so it's YZX actually. And so now we have this cool looking thing over here. Let's zoom in a little bit on that. So let me go all the way down to the main image. And well, I can zoom in actually over here by changing the zoom level. So I can make the zoom level or my field of view change it. So if I increase my zoom level, then I go in there. What I can also do is just move the camera closer. So I can go over here and say times 0.8 or 7 or 6 or whatever. So this is not the same as zoom. This is just getting the camera closer. Okay, so that works. Now let's go back to the gyroid. So the gyroid has an outside and it has an inside here, right? So the outside is where you have empty space where you could fly into it, and the inside is the solid part over here. Now I can make the inside also an outside by using an absolute. So if I throw an absolute around here, now it makes the outside also an inside. And right now that looks a bit weird because now we have an infinitely thin surface. And so we have to give that some thickness by subtracting something from here. And now we have a cool looking membrane like this. And there's still some glitches here sometimes where it kind of traces through the surface, and that's because this is not an exact distance. We have to make this a little bit more conservative by multiplying this by a number slightly smaller than 1. So 0.7 I think works fine, and that will get rid of any issues that we had before. All right, so I can make this maybe a little bit thicker. All right, so that's that. And now what I want to do is, so I basically made the gyroid that started out having an inside and an outside, and now I made the surface of that like where it goes from solid to non-solid, or made that into a membrane by kind of taking one side that was negative, making it positive, and then sucking it out a little bit to give it some thickness, which is what this is over here. And we can do the same thing to the ball itself. So, because right now we're taking the Boolean intersection of a solid gyroid that goes all the way and a solid ball, and so that's why it looks like this. But if I take the intersection with not a solid ball but with just a shell, then we get something like this. Go over here, say okay, ball, and again let me just show one more time here. So what we're doing, if we have the sphere by itself, for any point outside of the sphere, like the distance function is going to return a positive distance. As you get closer to the sphere, my positive distance is going to get smaller, smaller, smaller until it hits 0. And then inside of the sphere, it just goes negative, and it becomes a larger and larger negative number as you go inside. But if we take the absolute of that, then it goes from something to 0, and then from 0 back to something positive. And then we have an infinitely thin sphere that's going to give us some glitches, so we have to subtract a little number from it in order to make that solid. So now we're looking at a solid shell of a sphere actually, And now if we do the Boolean intersection, we get this cool looking object, which is pretty neat. Okay, so the next thing I want to do now, because right now I have a hard edge between the surface of the sphere and the surface of the gyroid. I want that to be all nice and round. And so this uses a max function. Well, we can make a smooth max function that can round the corners off for us. So let me make that. And actually I'm going to make a smooth min function, because the smooth min function can be turned into a smooth max function by just changing the sign of the third parameter. So I'm going to go through this quickly as well. I made a video also specifically about this function, so if you want to know what I'm doing here, then I highly recommend checking out the video in the description about smooth minimum. But for now I'm just going to make it, so I'm going to say float h is clamp, something clamp between 0 and 1, and then what do I have clamped? It's 0.5 plus, I gotta think about this, 0.5 times b minus a divided by k, and then I'm going to return the mix of the two functions of b and a with that parameter h that I just made, minus k times h times 1 minus h. Okay, so that should be that. So now we can, instead of using this max function here, I can use this smooth min function, and the smooth min function has that third parameter k, which indicates the smoothness that I want. And because I want to use a smooth max and not a smooth min, I'm going to make my k value negative. And if you can make your k value negative, then that turns into a smooth max. And you can already see it a little bit on the edges right now. It's like not hard anymore. And so now I can make that softer by increasing this. Okay, so now 0.3, and look at that. Now we have this super nice, smooth, sanded, rounded off shape, which is really, really cool. And looks very much like some sort of coral or something. Okay, next thing I want to do here is I want to make sure that my camera cannot go under the ground plane. You see right now it goes under the ground plane. It kind of screws things up. So let me just go down here in the main image. Here I'm setting my camera position, and here I'm doing the rotations of the camera. So the up and down and the left and right rotation. So after I do the up and down rotation, I just need to make sure that if ro.y gets smaller than some value, it gets clamped at that value. And the way I'm going to do that is I'm going to say max minus 0.9 and ro, and then I'm going to say ro.y equals that. So this just says that if the y position of the camera is smaller than minus 0.9, then this max function is going to return minus 0.9. And why minus 0.9? Because my origin is in the middle of the ball and the plane is at minus 1. Okay, so now if I do this and I go down to the ground, now it will not go through the ground, it will just kind of come closer like this. Which is pretty cool. All right, so the next thing I'm going to do is I'm going to put a light inside of this structure. And the way to do that is inside of where I'm doing my material rendering. So over here, this is my ray marcher. That just determines the distance from the camera to the scene, to wherever it hits the 3D objects. And then here it determines, okay, well, if I have hit a 3D object, well, then I need to do some material properties. And inside of here, I calculate the diffuse lighting based on this direction, and that's just a standard uniform light direction. Like in the case of if you had a sun, if you're outside and you have a sun, then the light angle doesn't change depending on where you are. But what we want is a point light that's in the middle. And so to do that, I have to make let me just call this light direction. I have to make a vector that for every point P, right? So if I'm in here, then I supposedly hit something. Let's say I hit like a pixel here on the ground. Well, now I have to calculate what is the vector from this point on the ground to the light source, and the light source is going to be at the origin at 0, 0, 0, right in the middle here. And so to do that, I can just say, well, here, light there. The light direction is just, well, this position P is a 3D position in relation to the origin, right? So if I just did P, then that would already give me the vector that goes from the light all the way to the point. But now I don't, like, I want the opposite of that. I want the vector that goes from the point to the light direction. Well, for that I can just make it negative. And then I need to make sure that my light vector is normalized, that it has a length of 1. So I can just say normalize here. And now I should have light on the inside. So this is what the shading would look like if the light is right inside, which is pretty cool. Now because right now it's really hard to see where this ball actually touches the ground because there's no shadows. So let's try to make a shadow, and for that, well, first off, I'm going to make a distinction between the ball and the ground. So the ball itself is never going to get any shadows because the light is inside of the ball and there's nothing else outside that can cast a shadow on the ball. So the shadows are only going to be on the ground. And so what I can do here is I have to determine whether I hit the ball or I hit the ground, and for that I can just get the distance from my hit position to the origin. Because if the distance from the hit position to the origin is larger than the radius of this ball, then I know that I haven't hit the ball, but I hit something else. And so let me also make a variable over here, float, call it CD for center distance, and that just gives me the length of P. So this is the distance from the origin. And because here I could say, well, if the distance from the origin is larger than the radius of the ball, which is 1, well then I know that I hit the ground instead. So over here I could say col times equals vec3, let's say a red color, so I can just make the ground red. And now you can see that the outside of the ball is also red, is because that's actually, this 1 was actually where the center of the shell, where the surface of the ball was before I split it into a shell and give the shell some thickness. And so I have to compensate for that as well. And the thickness of the shell is 0.03. So if I want to do this correctly, I have to add 0.03 here, so that we have the ball has a different color from the ground. All right, but I don't want this to be red. I just want there to be a shadow here, right? So now how do I do that? If you checked out the Ray Marching for Dummies solution or video, in there I talk about casting a shadow, and the way it would work is that you go from the hit position and you do another ray march in the direction of the light, and then you see how far did you march before you hit something. Because if you march less far than the distance to the light, then you know you hit something in between. Which is a general solution for shadows, but because this is such a nice constrained scene where there's only one light source and there's a sphere around that light source that's just casting shadows out, we can do that in a smarter way. So what I'm going to do instead, to figure out whether a point on the floor is in the shade or not, is I'm going to first make a vector that goes from the point to the origin, which actually we already have. That's light there. And then I'm going to, and so that's a vector that goes through the edge of the ball here. And then I have to, and so somewhere on that vector, if I go exactly at the right distance, then I'm exactly inside of the edge of the ball, and then I can check there, I can check the gyroid there, and if I evaluate the gyroid at that point and I'm outside of it, then I know that this point is in the light, otherwise that point is in the shade. So let's do that. So what I'm going to do here is I have, well, basically that point that is halfway between the point on the ground and the center, I already have that. That's this normalized P over here. Because the P is the vector that goes from all the way from the center all the way to the point, and the normalized version of that is that vector at a length of 1, which is somewhere inside of the boundary here. Just that my light there went negative, but for this it would have to be positive. So what I can do is if I evaluate the gyroid exactly at that point, which is minus light there, well, it's normalized P, okay, that's the point, but we already have that over here, so we can also say it's minus light there, and let's call this S. Then we should be able to use that to make a shadow. So let me have a quick look and see what that looks like. So col times equals S, let's say. And now you can see that actually gave us some shadows, because wherever it's black, that's where it's in the shadow. Wherever it's gray, that's where it's supposed to be in the light. It's just that right now these are distance values, and we need to cut out a sharp shadow from that. So, well, that's easy enough. We can just go float shadow equals, I'm just going to use a smooth step for that, and then I'm going to cut that out at whatever. I can do minus 0.01 and 0.01 just to see what that looks like, and then cut out with the shadow like that. And now we have a shadow that was very cheap to calculate, which is always good. Let me, and also I can make the shadow blurry, so this is kind of a soft shadow, right? Because I can play with this to make it more blurry. And so let's do that. Let's call this W over here, and this minus W. And so now I have a value W that I can change, right? I can make sharper shadows like that, or I can make blurrier shadows like that. And now what I want to do is I want to make it that the shadows get sharper as you get closer to the light source, and blurrier when you get farther away. And so for that I can just use this CD, or center distance. So if I go over here, CD, well, right now it's too blurry completely, although you can see a tiny little bit over here. But if I just make this smaller, times 0.1, let's say, and you can see that that's starting to work, right? You have a sharper shadow over here that slowly blurs out. Let me see here. If I do it times 0.02, yeah, that works pretty good. So now we have a sharper shadow over here, and it gets blurrier as you go away, which is kind of cool. And now the next thing that I want to do is I want to be able to not see all the way to the end of the plane here. So let's make that all nice and dark. So I can just I can just divide my color by my center distance to make that darker. Okay, and now, yeah, you can still see the edge here right now. So let me just divide it by the square of that distance. So by CD times CD. And that gives me a nice mysterious dark fall off. All right, the next thing that I'm going to do is I am going to add some waves on the ground here, so it's not completely flat. So let's have a look here. So that's for the ground here. So let me make another variable here, call it Y. That gives me my offset from the ground, and that could be, for instance, the sine of p.z like times some smaller value because it's going to get too large. And then I have to add that to my ground. So ground plus equals y. And you saw something change there. If you can't, like, if it's not too obvious, then we can just multiply this here to make it so that those waves go faster. So that's one way that you could do, right? You could like put a bunch of signs on top of each other. I am not going to do it like that. I am going to use another gyroid, because why not? So I'm going to say dot the sine of p and the cosine of p dot yzx, and let's see what that gives us. Okay, so for that also we have to multiply this p here. So because I'm not using that value p anymore down here, I can kind of screw around with it over here. It doesn't really matter that much. So let's say times 5. And now we have some bumps, and let's use an absolute on this so that we can get some ridges going. And yeah, so we can play around with this, because like this is going to be different when we change our y value. So if I do this, you'll see that it changes. Actually, let me just do that. You see that it changes. Okay, now we gotta find an interesting part here. Let me see. Because this just oscillates between waves one way, waves another way, and somewhere in the middle it kind of looks maybe a bit more interesting. Anyways, so that's one thing that you can play with. What I'm going to do is I'm going to vary that by a sine of p.z, let's say p.z, and then only maybe by 0.5. All right, well, I just have to see here, I want this thing to move, and I want it to move across the wave, not along the wave. So let me just make it move first. And for that, let me first just rotate the ball. Okay, so I want the ball, no, actually, let me first move it. So I'm gonna go over here. I'm gonna go p.z plus equals t. And I see that moves in one direction. I actually want it to move in the other direction, minus equals t. I also don't want it to move that fast, so let me just go to my t over here and make that go a bunch slower so we can appreciate it a little bit better. Okay, so now we have that the ground moves. Now we need to have it that the ball rolls at the same time. So for that, I'm going to go inside of this ball gyroid function here, and I'm going to rotate it. And because I'm going in the z direction, so if this is my z direction and this is my y direction, where y is pointing up, then I need to rotate. I need to rotate the y and the z, okay? Because I'm going to rotate it like that. And so I'm going to do here yz times equals the rod of t. And now we have a ball that rolls at exactly the right speed. And why is that? Well, that's because my ball has a radius of 1. And if it has a radius of 1, then it just comes out that that the rotation and the movement exactly are at the correct speed. So that is pretty cool. Over here I see a tiny little bit of tiny little bit of glitchiness, so maybe we want to fix that by making our step size slightly smaller. You got to be careful though with this, because your stuff gets a lot slower if you do that as well. So let me just do times 0.9. That should probably fix it. Yeah, okay, so that's that. Let me see here. Yeah, so that's that. I think I'm going to leave it here for the first video. In the second video, we're going to do all kinds of cool special effects on top of this. So, so yeah, be sure to subscribe so that you don't miss the next video. And either way, I will see you